right, so we're going to transition to a different type of function, and these are rational functions. So we're going to talk about rational functions, the graphs, and all the different characteristics of rational functions. We talk about these right after polynomials because literally a rational function is a ratio of polynomial functions. So it's a polynomial on the top, polynomial on the bottom, and because it's a fraction, that's what makes it a rational function. So a lot of the stuff we talked about with polynomials will come in handy as well. The good news is that there won't be synthetic division and all of that hot mess that you saw in that last section there. I know it's complicated, and there's just a lot of moving parts. So here's a graph of a rational function. What you're going to see rational functions have is they have kind of these curves going on, and they have some important characteristics. A lot of rational functions can have what we call a vertical asymptote. And so a vertical asymptote is a vertical spot in the graph where your graph is going to get closer and closer and closer to it, but it's never actually going to get there. So as this graph goes down forever, it's getting closer and closer and closer to this vertical line here, but it's never actually going to get there. The same thing's happening on this side. If you could imagine this graph going up, it's getting closer and closer and closer to a vertical line there, but it's never actually getting there. And so what's happening here is at 4, this graph doesn't exist. Your graph is behaving where it's either going straight down or straight up, but that specific number doesn't exist. And it doesn't exist because in the equation, it would have divided by 0. So there is a vertical asymptote here. It is at x equals 4. A horizontal asymptote is the same idea, except for instead of running vertically, it runs horizontally. One of the main differences, though, is that you cannot cross a vertical, but you can technically cross a horizontal. You don't have to cross it, but you could. But what's still happening is as your graph is going out and it's going forever this direction, it's just going to get closer and closer and closer and closer, but it's never going to actually get there as you go forever, all right? It's just the values are going to get closer and closer. Same thing here. Imagine that this is heading this direction. It's going to curve out and start running really close, but never actually getting to that horizontal asymptote. And the value of that horizontal asymptote is a y value. That's y equals 3. So make sure if they ask for asymptotes that you clarify if it's an x equals or a y equals. If you just say 3, they're going to mark it wrong. If you just say 4, they're going to mark it wrong. It has to be x equals 4 or y equals 3. You have to be specific there. All right. In terms of the domain, remember domain is talking about all of your x values. All of these values are included. All these x values have a spot on the graph. The only one that doesn't is here at 4, and that's because at 4 there exists a vertical asymptote. So your domain is literally everything until you get to 4. 4's out. And then after 4, because this graph is going up this way, it's literally everything after 4, and it continues on forever. So if you remember, if we're going to say anything but 4, you would say negative infinity to 4, union 4 to infinity. This reads everything negative infinity to infinity with the exception of 4. 4 is excluded here by doing this process in the middle. All right, x-intercepts and y-intercepts, you probably don't even need me to explain those. That's where it crosses the x-axis and the y-axis at, right? So here would be an x-intercept that's at negative 1, 0. Why did I put it as a coordinate point? Because intercepts should always be written as coordinate points. The y-intercept, that's here. I know it's a little off, but we're going to say that that's 0, negative 1. All right. So x-intercepts, y-intercepts, those shouldn't be anything new. Technically, we've talked about domain before, so now we're adding in these ideas of asymptotes. So if you want to give it a shot and see if you can pull the pieces of information from this, go for it. Just hit pause and then you can come back to the video. All right, so I'm going to start with the vertical asymptote. There is very obviously one here at negative 3. It's marked, so we would say x equals negative 3. And then there is another very obvious one here at 3. It's also marked, so that's also x equals positive 3. Both of them are x equals because they're vertical. They cross the x-axis. And so what's going to happen here is your graph is going to get close coming this way, close coming this way, never actually meet, never actually get there. Same thing on this side. It's going up and getting close, and this one's going up and getting close as well. All right, your domain is all about your vertical asymptotes and one other feature that we haven't seen yet, but we will talk about briefly. And so the domain is everything but these two numbers. All these values are included in this part of the graph. All of these values here are included in the middle section of the graph, and then all of these values are included in this part. So the domain would be negative infinity to the first issue at -3, union -3 to the next issue at 3, and then union 3 to infinity. All right, we're going to jump back to the horizontal asymptote. I don't see any horizontal dotted lines, but that doesn't mean that there isn't one. It's about what's happening at the ends of your graph. So take a look at the end here. What is happening if you imagine this being drawn out? It's going to turn and run flat, isn't it? And it's going to run along the x-axis. On this side, imagine this keep going. It's going to run along the x-axis as well. And so that does mean that there's a horizontal asymptote, even though there's not a dotted line written on our graph. They don't have to put the dotted lines in there to represent asymptotes. It's all about the behavior of the function. And so there is a horizontal asymptote. It's a y equals, and if it's on the x-axis, that's where y is equal to 0. All right, last but not least, x-intercepts, y-intercepts. You should be okay with those as long as you remember to put them in coordinate points. X-intercepts, it crosses right here at 1. So that would be 1, 0. I don't see any others. Y-intercept, that's right here at -1. So that's going to be 0, -1. And there can't be any more. There's only one y-intercept. All right. So what we're going to do now is we're going to talk about how to find all of these things, but without a graph. Instead of having a graph, you have an equation. All right, so here is literally how we find everything. How to find everything. So this would be really good for your notes in terms of like having this kind of like as a go-to where you can see it really easily as you're working through these problems in your homework problems. So the domain is going to be everything except for you're going to check for where the denominator is equal to 0, because what you cannot do is you cannot divide by 0. So it's everything but where denominator equal to 0. Everywhere but there. The y-intercepts, if you ever want to find a y-intercept, all you have to do is you have to plug in 0 for your x's. Every single x turn into a 0 and do the calculation. It'll tell you the y-intercept. And then one other thing, make sure you write it as a point, coordinate point. If you don't put it as a coordinate point, it's going to mark it wrong. All right, x-intercepts, those are a little bit harder to find. The x-intercepts are going to happen where the numerator is equal to 0. So check out where the numerator is equal to 0. Tell you your x-intercepts. We have a new thing here, the x value of any holes. We haven't talked about holes in the graph. And holes are going to happen when the denominator is equal to 0, but the numerator is also equal to 0. So for the holes, it's going to make both the numerator and denominator equal to 0. Both the numerator and denominator. And we will see examples. So if you're like, I don't know what you mean by that, we'll see examples. Both. Vertical asymptotes, they're going to happen where the denominator is equal to 0. So if you have a denominator equal to 0, for some number, it's either a whole or a vertical asymptote. When the numerator is equal to 0, it's either a whole or an x-intercept. The wholes is what makes them both equal to 0. Any left over in the numerator, those are x-intercepts. Any left over in the denominator, those are vertical asymptotes. All right, we have a horizontal asymptote at y equals, and what I'm going to do is I'm going to direct you, so draw an arrow over to this chart on the next slide, and this is going to talk about how to find the location of horizontal asymptotes. So blah, 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 there's a bunch of stuff at the top that just says, hey, horizontal asymptotes, you got to have a rational function with polynomial over polynomial, all that fun stuff. And then these are your three options, okay? If the degree is the same of the top and the bottom, that's what it's saying here. The degree of p of x, that's the top. The degree of q of x, that's the bottom. If the degree is the same, then you're going to have a line, y equals a over b, where a is the leading coefficient of the top and b is the leading coefficient of the bottom. And we will see examples, I promise. If the degree of p is less than, so the top is less than, then it's going to be at y equals 0. If the top is greater than, then there is no horizontal asymptote. And we will see these. So what we're going to do is we're going to compare the numerator and denominator. We're going to compare the degree, so the highest power. If they're the same, then we're going to use the coefficients. If the top is, well, I guess a better way to say this, if the bottom is bigger, it's at y equals 0. If the top is bigger, then there is none. All right, and last but not least, we have a oblique asymptote, and so for that, I want you to check out this table over here. So an oblique, by the way, could also be called a slant asymptote, and then they never call them this, but we should think of these are diagonal asymptotes. So we have vertical, we have horizontal, and then there is such thing as a diagonal asymptote. They don't call them diagonal, they call them slant, or they call them oblique, one of the two. So here's how you would find a slant asymptote. It only happens when the degree of the top is exactly one more than the degree of the bottom. So if that is not the situation, then automatically there are none. But if the top is exactly one more than the bottom, then what you're going to do is you're going to do some dividing. You're going to get the quotient obtained by dividing, and whatever you get for your quotient, that is where your slant asymptote lies. And once again, we will see examples, I promise. I actually have I have 3 examples of how to find everything. All right, so here is the first one, and this carries over. If you notice, it goes 5, 6, 7. So these are the same polynomial or rational functions, and we're going to find all 7 pieces for this. All right, so your domain, if you go back up, is everywhere but where the denominator is equal to 0. So for the domain, we need to figure out what makes the denominator equal to 0. And this shouldn't be that hard because this is just a linear function. You would subtract 9, divide by 5. So we would say x cannot be negative 9 over 5. If you plug in negative 9 over 5, you'll get a 0 in the denominator and we'll divide by 0. And that's not, you can't do that. Not an option. So it can't be negative 9 over 5. We need it in interval notation. So we'll say negative infinity to negative 9 over 5, union negative 9 over 5 to infinity. All right, the y-intercept, if you go back up, it says plug in 0 for x, and remember to put it as a coordinate point. So if you plug in 0, let's talk about what happens. You'll have 7 times 0 plus 3 on the top, and 5 times 0 plus 9 on the bottom. 7 times 0 is 0, plus 3 is 3. 5 times 0 is 0, plus 9 is 9, and they actually simplify to 1 over 3. So your y-intercept is at a coordinate point 0, 1, 3rd. All right, up next, the x-intercepts. If you go back up to the x-intercept, it's where the numerator is equal to 0. So now we're going to check the top. Where is that equal to 0? you would subtract 3 and divide by 7. So that would be at negative 3 over 7. And then you do just have to make sure, does negative 3 over 7 make the bottom equal to 0? Well, we said no, it didn't, right? So that means it is just an x-intercept. So its coordinate point would be negative 3 over 7, comma, 0. All right, up next is the wholes. So wholes make both the numerator and denominator equal to 0. So is there a number that made both the top and the bottom equal to 0? Well, the bottom was equal to 0 at negative 9 over 5. The top was equal to 0 at negative 3 over 7, and those are not the same number. So that means that there are none. It is possible to have none. All right, up next is the vertical asymptote. That is where the denominator equals to 0. So now we're on this side over here. So where was the denominator equal to 0? Well, we already figured that was at negative 9 over 5. So the issue in the domain is there's a vertical asymptote at negative 9 over 5. They already, if you notice in here, they already have x equals, which is why I didn't put x equals. But if that was missing, we would have to put in the x equals as well. All right, horizontal asymptote. So go back up. For the horizontal asymptotes, you should be looking at this here. And what we're checking is the degree of the top and the degree of the top of the bottom. So the top has a degree of 1. The bottom has a degree of 1. So they have the same degree, right? Top and bottom are the same. They're both powers of 1. So what we're going to do is we're going to look at just the coefficients in the front, the numbers in front, and that is 7 over 5. So it's actually this first option up here. They're the same. It's at y equals 7 over 5. So since this is the same degree, it's y equals 7 over 5. So you'll just plug in 7 over 5 because it already says y equals here in the front. So 7 over 5. All right, and last but not least, the oblique asymptote. So for the oblique asymptote, you're going to go number 7, which means talk about this one or look at this one. And for this to happen, the top has to be exactly 1 more than the bottom. So the degree has to be 1 more than the bottom. So if the degree of the top is 1 more than the bottom, then we'll have to keep going. If not, then there is none. So because they're the same, that means there's none. By the way, when you do this, you either have a horizontal or an oblique, slant, diagonal, whatever you want to call it. You cannot have both. You either have one or the other, or it is possible to have none of them. All right, a few more examples here. So this next one, sorry, you can't see it. There's actually an x squared in front of that. X squared right there. So it's x squared minus 5x plus 4, x squared minus 3x minus 10. Because they're both quadratics, and I'm going to be needing to figure out where things are equal to 0, it's actually in your best interest to go ahead and just factor it from the get-go. So factor the top, factor the bottom, and then that's going to make it a lot easier to find all this stuff. So multiplies to be 4 adds up to be 5 would be negative 1 and negative 4. And the bottom multiplies to be 10 adds up to be negative 3 would be negative 5 positive 2. All right, and you can have this out so we can kind of keep going back to it as needed. So the first question is the domain. That's everywhere but where the denominator equals to 0. So what numbers make the denominator equal to 0? That's 5 and negative 2. So it cannot be, right, 5 and negative 2. Has to be written in interval notation. So negative infinity to negative 2. Negative 2 then to 5. By the way, don't skip the stuff in the middle. It's included. There's no issues with the stuff in the middle. Some of us just do this and then they jump straight to the 5 to infinity. There is stuff there, and it's part of the domain. You can plug in 0. You can plug in 3. You can plug in 4. You can plug in the decimals in between them. They're included. All right, for the y-intercept, if you go back it says plug in 0 for x, and we're looking for a coordinate point there. When you plug in 0 for x, you can plug it into either one. It's up to you. I like to plug it into the first one because 0 squared is 0. Negative 5 times 0 is 0. So the top is just 4. If you plug it into the bottom, 0 squared is 0, minus 3 times 0, still 0, minus 10. So the bottom is negative 10, which would simplify to negative 2/5. So it's at the coordinate point 0, negative 2/5. All right. Part 3, find the x-intercepts. By the way, the x-intercepts, holes, and vertical asymptotes, the question over here, they all go together. So it's actually easiest if you find the holes first. So are there any matches in the numerator denominator? Are there any factors that match? And by match, I'm saying like, hey, there's an x minus 1 on the top and an x minus 1 on the bottom. Or there's an x plus 2 on the bottom, there's an x plus 2 on the top. Like they match exactly. And there's no matches. And so since there's no matches happening, then there's no place or there's no x value that makes both the top and the bottom 0. And so you almost want to make sure you do the holes first, because if there is a hole, then it doesn't include in the other ones. So no holes, because there's no x value that works for both the top and the bottom. They don't have the same factors. So x-intercepts are going to be, if you go back to your how to find everything, where the numerator is equal to 0. So what two numbers make the numerator equal to 0? Well, that's 1 and 4. Make sure you list them at coordinate points 1 and 4. All right, the vertical asymptotes, I'm going to zoom out a little bit. So vertical asymptotes over here is where the denominator is equal to 0. So go back to your denominator. That's 5 and negative 2. And I didn't put x equals for these because there's already an x equals in the front. If that wasn't there, you'd have to put x equals. All right, up next is the horizontal asymptote / oblique asymptote. You either have one or the other, or you have neither. You can't have both. So in order to figure out the horizontal asymptote, you're looking at this chart and you're deciding, is the power on the top the same, bigger, or smaller than the one on the bottom? So the highest power here on the top is 2. Highest power on the bottom is also 2, so they are the same. And when they're the same, you go to the coefficients in front of them. Well, that's a 1. That's also a 1. And so the horizontal asymptote is at y equals 1. 1 divided by 1 is 1. And so you don't have to write same in here. You would just put y equals 1, knowing that they're the same. Oblique asymptotes happen when the power in the top is 1 more than the bottom, and they're the same. So that means that this is not happening. There is none there. All right, we have one more example, one more polynomial function, or rational function, that we're going to find all the important pieces of information for. So we're going to go ahead and start by factoring both the top and the bottom. The bottom's pretty easy to factor, right? -6 and -1 to make -7. The top, they all have an x in it. So this is an x cubed, but luckily they all have an x. So you can actually take out the x, and then what's left over after you take out an x is an x squared minus 4x minus 5. And we can get that to keep factoring as x minus 5 and x plus 1. And so I'm just going to cross that off so I don't get distracted by it. So here's it completely factored. All right, the domain, what makes the denominator equal to 0? That's 1 and 6. So 1 and 6, it cannot be those two numbers. So we'll say negative infinity to 1. Union 1 to 6, don't forget the stuff in the middle. Union 6 to infinity. For the y-intercept, you're going to plug in 0 for x. So if you do that, you'll have a 0, and a 0. So the top is 0. The bottom is 0, 0, and 6, and 0 divided by 6 is 0. So your y-intercept is at 0, 0. All right, x-intercepts, holes, and on the next slide, the vertical asymptotes, those all go together. And like I said before, do the holes first. Are there any matches here? Are there any numbers that make both the top and the bottom equal to 0? And for that to happen, they have to have the same factors. And so there's no matching factors, which means that there's no holes. So what's left in the numerator makes your x-intercepts. What's left in the denominator makes your vertical asymptotes. So your x-intercepts would be at 5, -1. And then don't forget, there is an x in the front. And so you can make the entire numerator equal to 0 by plugging in 0. And so that's 1 as well. And you do have to write them as coordinate points. All right, vertical asymptotes on the next slide, essentially. Vertical asymptotes, that's what makes the denominator equal to 0. So that would be 6 and 1 or 1 and 6. It already has the x equals in there, so I don't have to worry about including that. All right, and then horizontal asymptote, take a look at the powers. We have a power of 3 and a power of 2. So if you need to go back, the top is bigger, right? The degree of p of x, that's the top. The top is greater than the bottom, so that's the bottom, this last option here. So what it means is it has no horizontal asymptotes. So this is none. Oblique asymptotes happen when the top is exactly 1 more. So is the top exactly 1 more? Unfortunately, the answer is yes, which means that there is an oblique asymptote here. So we are going to go ahead and have to find the equation for this oblique asymptote. And here's how you do it. You divide these. So back a few sections ago when we did some long division, we're going to have to do that again. 4x squared minus 5x. So we need to long divide these. What we get here when we're long dividing, that is going to be our oblique asymptote. So x squared times what is x cubed? Well, that's x. Carry it through, we have x cubed minus 7x squared plus 6x. And if you remember, you have to subtract everything there. So we'll have 0, we'll have -4 plus 7, so 3x squared, and then we'll have -11x. And then you keep going. X squared times what is 3x squared? Well, that is times plus 3. And then technically you can stop here. And your oblique asymptote is just x plus 3, what's up here at the top. And I know I can stop it because this is the equation of a line. So an oblique asymptote is a line, a diagonal line. And so x plus 3 is the equation of a diagonal line. Also, I know that when I did this, I did x squared times what is 3x squared. And so when I got to the constant, that means there wasn't going to be any more to add. I could multiply this out, get what's left over, but what's left over would just be my remainder. And so I don't even need to pay attention to the remainder. It is just x plus 3. The equation is y equals x plus 3. Notice the y equals is already built in there. All right, that is it for this section. So let me know what questions you have, what I can do to help you with your MyOpenMath. Feel free to message me, all that fun stuff.